So now that we have a pretty good sense for three-dimensional structure of molecules, we can think about how electrons are distributed throughout the molecule. And I'd alluded to this in a previous video, but a lot of the chemical and physical properties that we observe for molecules are based on how the electrons are distributed. And the example that I was talking about previously was HCl. Remember when we talked about bonds and the nature of bonds, we said that they could be anywhere on sort of a big continuous spectrum. They could be completely covalent, meaning they were nonpolar. The electrons were perfectly shared amongst the two atoms. That's all the way out here. Or they could be completely ionic, meaning electrons are completely given from one atom to another. And we said those are the sort of binary extremes, but the vast majority of molecules lie somewhere in here, and we call these things polar covalent molecules, or polar covalent bonds. And I also alluded that if you have a molecule with multiple bonds, we could think about the polarity of the entire molecule. So if we think about HCl to begin with, this is really simple because it's a linear two-atom molecule. So the bond really is the molecule itself because we only have one bond. But remember, we said that based on differences in electronegativity, we could assess where molecules lie or where bonds lie on this continuum. And we said anything that had greater than 2 units of electronegativity difference, we called those ionic. Less than 2, we said they were polar covalent, and 0, we called those completely nonpolar. So HCl is somewhere just less than 2. So this is a polar covalent molecule. It's definitely on the high end, closer to ionic. And then we said that we use this these symbols, the lowercase Greek delta, to denote where sort of the electron density lies. And we call these partial positive and partial negative charges. So in this molecule, the chlorine is much more electronegative. Electronegativity is pointing this way, which, remember, electronegativity is just the propensity for an atom to draw electrons towards itself. And so we said, in reality, if we looked at an electrostatic diagram, you know, a sort of hypothetical picture of where the electrons lie, it would be something like this, where we'd have much of the electron density over here on the chlorine, and you'd have this sort of more positive character on the hydrogen. So now let's extend this to a multi-atom molecule. So let's think about something like methane. We know, we've thought about methane a lot now. Methane has this tetrahedral structure that looks like this. And we could look at the polarity of each of these bonds and assess where it lies on this scale. And what we'd find is that each of the bonds has more of a partial positive character on the hydrogens, and more of the electron density is being yanked towards the core, towards the more electronegative atom. And we can use this type of nomenclature or symbology to represent sort of the directionality of the polarity of the bond. So I draw this arrow and then I put a dash at one end, and that dash at that end denotes, you know, where the more positive part of that bond lies. And so when you draw this red arrow like this, it says that the hydrogen is more positive and the electron density is pointing towards the carbon. So we could do that for all of these bonds, right? Because they're all the same. And the question would be, is the molecule polar? We know that the bonds are definitely polar. There is a difference in electronegativity between hydrogen and carbon. But when you have a completely symmetric tetrahedral molecule, all of these polar bonds are canceling each other out because they're equal and opposite. It's a completely symmetric molecule. So if it's symmetric, even though the bond is polar, the overall molecule can be nonpolar. And that's a really interesting concept. So let's think about, what if we replace one of these hydrogens. I'll just erase, if I can do this, I'll erase one of these hydrogens. I'll erase this one. What happens if I erase that hydrogen, and instead of that hydrogen, I replace something that's more electronegative than carbon. So I put maybe chlorine here. So this is chloromethane, the molecule. Chlorine is further up right on the periodic table, which means it's more electronegative. So in fact, if I were to draw the symbology here, I would actually pull the electron density out towards the chlorine. And so that's different than the other three bonds, in which case we disrupted the symmetry. This is no longer symmetric. In fact, we have a much polar bond here, and in reality, the overall electron density would be pointing a net direction up this way. So let me paste in a picture of what the electrostatic diagram would look like. So you can see the electrostatic diagram, because we have a much more electronegative atom pointing up at the top now, the overall net polarity of the molecule is pointing up here towards the top. We call this net polarity. If a molecule actually has net polarity, we say that that molecule has a permanent dipole. So dipole is related to a molecule. So when we're talking about polarity, typically we're talking about polarity of an individual bond. But when we add up all of the vectors of the differences between electronegativity in the atoms in a molecule, and if that turns out to give you a net difference in one direction, then we say that molecule has a permanent dipole. And we say the molecule itself is polar. This has huge implications, and we may get to this in chapter 11, where we talk about how molecules with similar polarities tend to dissolve in other molecules with similar polarities. And that's what we use as a principle for solubility, is based on what molecules have permanent dipoles. I'll just compare a couple molecules here. So this table on the left just represents some common molecules and their dipole moment. You can actually calculate this. It's not important that we be able to do this in this class, but it's nice so that we can compare these things quantitatively. We see at the top NaCl, that's a completely ionic compound, so of course it has a really large dipole. And then down at the bottom we have carbon tetrachloride, or CCl4, and we can draw that out, and we know that because that has 4 charge clouds like this, if we draw the Lewis structure, it's going to look like this. We know that the polarity of each of these bonds is pointing out towards that more electronegative chlorine atom, but it's completely symmetric. So all of those vectors, those polar vectors, cancel each other out, and that gives rise to this this zero dipole moment. Similarly, with CO2, it also has 0. We know that the structure for CO2 looks like this. We know that oxygen is going to be much more electronegative, so we would end up having a structure that looks like this, but these are equal and opposite poles, and so the net dipole of this is 0. Got some structures here for ammonia. You can see how ammonia is here on the table. It's 1.47. That's because of the electrons, this lone pair here, drawing charge upward more so than anything else. So that gives a pretty polar dipole moment. But then let's look at water. Water is actually quite a bit more polar. Why is water polar? Well, it's because it has that bent structure. Remember from our discussion of molecular geometry or shape, we've got these 2 lone pairs up here which are crucial for the shape of water, right? If those didn't exist, water would be linear, just like CO2. It wouldn't be polar, which means it would have huge implications for its properties. If water weren't polar, it wouldn't stick to itself nearly as much, which means that it would have a much lower boiling point, which means that we wouldn't have free water, liquid water, on the surface of Earth. It also means that it wouldn't dissolve salts, both of which would mean that we wouldn't have biological life on this planet.